Thanks again for having me here. I'm going to talk about using radiocarbon to look at fossil fuel CO2 emissions. And of course, we all know that any research that we do takes a lot of people to help with it. And so there are a number of other people who have been involved in this research. My team at GNS Science, doing radiocarbon measurements and atmospheric measurements. And then I'm going to show a bunch of data from the Influx project, which there are many people involved from a bunch of different universities. So I'll give a bit of an introduction to why we want to separate fossil fuel CO2 from biogenic CO2 in cities, and how radiocarbon works as a tracer. And then I'm going to just give two examples, one from the Influx experiment in Indianapolis and another one with this very long-winded name, the Great Greenhouse Gas Grass-Off, which is really looking at the very fine scale of how traffic emissions changed in New Zealand during the COVID-19 lockdowns. All right, so I think in this audience, everybody's well aware that all nations have agreed to reduce their emissions through the Paris Agreement and the UNFCCC and all of those international agreements. And then under that, most nations have produced their own pathways to how they're going to meet what they've committed to in these agreements. But what's really, really important about this for us from a city perspective is that even if the policy directives are coming from the national or international scale, a lot of the actual actions to reduce emissions are happening at the city scale. Cities are where emissions are happening, and that's where policy changes are typically enacted to reduce emissions. So if we want to be able to reduce emissions at the city scale, we need to know what those emissions are. We need to know how big they are, what the source sectors are, and whether the policy actions are actually being effective. So we really do need ways of determining those emissions. And obviously you've heard in the seminar series a number of ways to do that. So I'll be talking about just one of those. And really the challenge that we have, and I suspect that most people in this audience already know, is that just measuring CO2 concentrations alone can make it very difficult to infer what our fossil fuel CO2 emissions are. And that graph on the right there is an example of the blue line is the CO2 increase from the Mauna Loa record, showing that increase over time. But the reddish line there is what the CO2 increase in the atmosphere would look like if all of the fossil fuel CO2 emissions that we put into the atmosphere stayed there. And clearly you can see that only about half are staying in the atmosphere. And that's of course because we have exchange of carbon between the atmosphere and the land and the oceans, as well as the fossil fuel emissions. And those exchanges with the land and the ocean are of course very large relative. The gross fluxes in each direction are very large, even though the net fluxes for both the land and the ocean are relatively small. And what that means is if you just measure CO2 alone, it's really difficult to distinguish whether you're seeing fossil fuel emissions or whether you're seeing these other fluxes. And to give you an example of how that plays out, this is from the Indianapolis flux experiment, Influx. And what's shown here is data, flask measurements from 5 towers around Indianapolis over a period of 5 years. The grey points are a tower that's normally upwind of the city, seeing incoming air, and the coloured points are towers that are downwind of the city. And you of course see there's a gradual increase over time. That's the addition of fossil fuel CO2 over time, increasing CO2 in the atmosphere. Huge seasonal cycle, photosynthesis and respiration that's happening all over the continent. And then the signal that we're really looking for of what's happening in the city is the difference between any given grey point and the coloured points on the same day. So that biogenic exchange that's causing that huge seasonal cycle and also causes the daily cycle have a really big impact, and distinguishing the signal that we care about from that can be pretty challenging. And for a while, people sort of thought, oh, well, cities are covered in concrete. Maybe there's not much biogenic flux there. We don't need to worry about it. But we're really seeing that's not actually the case. And this is an example of a modeling study from Boston by Hardeman et al., where they modeled biogenic carbon fluxes in Massachusetts on the left, and then on the far right is sort of zooming into the Boston area. And you see, from their model, maybe the biogenic fluxes are smaller in the city itself, but they're still there. They're non-zero. And of course, those biogenic fluxes can vary a lot, seasonally and diurnally. And those biogenic fluxes can vary in kind of surprising ways. So the example on the left is a study from Los Angeles by John Miller and colleagues. And what's shown on the top is the biogenic CO2 mole fraction. It's not a flux that's shown there, but mole fraction measured in flask samples in Los Angeles over a year. It's actually several years of data that's normalized. And you see the seasonal cycle in that biogenic CO2 mole fraction. And that seasonal cycle shows drawdown in the summer months. Yes, July is summer in Los Angeles, get that right. And respiration in the winter, which initially is not surprising, but it is, when you think about it, surprising for Los Angeles and for California, because California is very dry in the summer. And on the bottom graph, it shows precipitation in red. And you see that the wet season in California is in the winter there. And so that is actually when you have more productivity and more growing going on in California in general. But we're seeing an opposite seasonal cycle in Los Angeles. And it turns out that the seasonal cycle in the biogenic CO2 that's seen in the city is really strongly correlated with water use, people watering their lawns in the city. And so if we were to assume that the biogenic carbon fluxes in Los Angeles were the same as the rural area around it, we would be very, very wrong. So we need to understand this. The second example on the right is some eddy covariance measurements from Auckland here in New Zealand. And there it's showing diurnal cycle of CO2 fluxes for the 4 different seasons of the year. And you see something pretty familiar. You see positive values of respiration at night. There's a bit of a morning rush hour peak, and then draw down during the day. I should say that this is from a suburban site, so the rush hour and fossil fuel signals are probably relatively modest there. But what you see here is that same pattern shows up all year, that there's not a really strong seasonality in Auckland. And that's different than we might have expected, particularly from all the experience in Northern Hemisphere cities that tend to have a strong dormant season in the winter. And cities like Auckland don't really have a dormant season. So there's all these different ways that those biogenic fluxes could play out. So people have been thinking about this problem for a while, and there's lots of different ways that we can separate the fossil fuel and the biogenic components. And many of you on this call have worked on some of those, but I'll just talk about one of them, which is radiocarbon. And so really the concept with radiocarbon is it's the radioactive isotope of carbon. It's produced naturally in the upper atmosphere. It quickly reacts to form radiocarbon CO2, 14 CO2, and it moves throughout the carbon cycle. Anything that's still exchanging carbon regularly with the atmosphere will have a radiocarbon content about the same as the atmosphere, but anything that's not exchanging with the atmosphere will gradually lose its radiocarbon through radioactive decay. And importantly, for us, fossil fuels have been out of contact with the atmosphere for millions of years, so they have no radiocarbon remaining in them. So this means that we have a tracer for the addition of fossil fuel CO2. We will see a change in the radiocarbon content of the atmosphere, a decrease in the relative radiocarbon content of the atmosphere. And we can quantify that and measure fossil CO2. So to just give you a bit more backstory on radiocarbon, because if I don't talk about the bomb spike, I'm sure someone's going to want to ask. So this shows the record of radiocarbon and atmospheric CO2 from Bearing Head here in Wellington. It's about 10 kilometers from my house. You see the photo there. And this record, the measurements started in 1954 and we continue them to the present day. We report radiocarbon in this delta 14C notation, sort of similar to the notation that people use for stable isotopes. So a value of 0 in this notation means that you have the same amount of radiocarbon as your standard. And in our case, the standard is approximates what the atmosphere looked like in 1950. If you double radiocarbon, you get a value of plus 1,000. And so what you see here is with the start of this record, the atmosphere looked like the atmosphere did in the 50s, and then radiocarbon nearly doubled in the early 1960s. And that is the addition of radiocarbon produced by atmospheric nuclear weapons testing. A lot of other radioisotopes which produced as well. If you look closely at this, you might note that the peak in this graph is in about 1965, which is a bit over a year later than the peak of the nuclear weapons testing. And that's because the spike happened in the Northern Hemisphere, and then it takes a bit over a year to exchange air between the Northern and Southern Hemisphere. So we see a bit of a delayed reaction, and also a slightly smaller magnitude of this peak. That peak decreases over time. That's way too fast for it to be radioactive decay of radiocarbon, which has a bit over 5,000-year half-life. And that's actually exchange of that newly created radiocarbon CO2 moving into the oceans and the biosphere. And once we get out somewhere beyond, around about the 1990s, the addition of fossil fuel CO2 is really the dominant driver of this continuing downward trend in radiocarbon content in the atmosphere. So in that early period around the bomb spike, radiocarbon was not a very good tracer for fossil CO2 because these other effects were really important. But more recently, it's really a tracer for fossil CO2. And we can take all the effects that we know about that work on radiocarbon. So we had a carbon cycle before, now we have a radiocarbon cycle. So we have exchange of carbon with the land and the ocean. Those are big exchanges, but the radiocarbon content is roughly, not perfectly, but roughly the same as what's in the atmosphere. So those have very little effect on radiocarbon. We're adding fossil fuel CO2 that has no radiocarbon in it, so it has a really big signal on the atmosphere. We also have the natural cosmogenic production of radiocarbon going on all the time in the upper atmosphere. And then, as I said, in the 60s, we had atmospheric nuclear weapons testing, which had caused a big increase in radiocarbon in the atmosphere. That's mostly gone away, but there is still a small effect from the nuclear power industry releasing radiocarbon. Depends on the particular nuclear reactor types and how they're managed. But that is important in some places, not too many places, but most notably probably the United Kingdom has quite an influence from nuclear power plants. So we can put all these factors together with what we know and look at how this looks in the world. And so this is some modeling work from when I was a postdoc at LSE in France, using the LMDZ model with radiocarbon in it to really show you that radiocarbon tracks fossil CO2. So on the left is in model world, fossil fuel CO2 emissions being transported around the world. And on the right is radiocarbon with all those effects that I showed in the last slide, all included in it. And I flipped the scale around because, of course, the radiocarbon content in the atmosphere decreases as we add fossil CO2. But what you see is that these two pictures look very, very similar, remarkably similar. The radiocarbon in the atmosphere, in the lower part of the atmosphere, really tracks fossil fuel CO2 emissions. And you see that very strongly in the Northern Hemisphere. You see all the big hotspots of emissions. If you've looked a bit closer, you'll note that the agreement is not so good in the Southern Hemisphere over the Southern Ocean, and that's because there is also a source of radiocarbon depleted CO2 coming out from deep water upwelling in the Southern Ocean. And that's something that we're also using radiocarbon to trace for, but that'll be a talk for another day. So for this talk, it's really about using radiocarbon as a tracer for fossil CO2. So a couple of examples. I'll start with the Influx project and what we can do in a city of using radiocarbon as a tracer. So the Influx project has been running since 2010. We've had 12 towers. We've actually had 15 different towers, but never more than 12 running at a time. We've also had aircraft flights, and we're making flask measurements for radiocarbon, CO2, CO, and also a whole lot of other species. So what I'm showing here is measurements of radiocarbon, CO2, and CO in flask measurements from a number of those towers in Indianapolis over since starting in 2010. And you see the colors go in and out as not all the flask sampling systems have been running for the full period. And you see in radiocarbon, you see this gradual decline as we keep adding fossil fuel CO2 with no radiocarbon, and then you see values lower than that, where we see more polluted samples, CO2, we see the increase over time, the seasonal cycle, and so forth. And then we see carbon monoxide on the right. So what we do is take this data and we look at the enhancements over background, or the excess. in these species. So that's what's shown in the bottom set of panels. So for fossil fuel CO2, we calculate it from radiocarbon using the equation I've given there, which is based on this absence of radiocarbon from fossil fuels. And we calculate the enhancement of the background, which in this case, we've used the tower that's upwind of the city, Tower 1, as the background. For CO2 and CO excess or enhancement, we're just looking at the difference between what we observe at a downwind tower relative to the background tower. And now a lot of that seasonality and the trends through time go away when you look at those enhancements. And we see consistent enhancements in all these anthropogenic species at the downwind towers, as we might expect. So these are enhancement mole fractions. What can we do with those? So the first couple of things we've done with it is to just look at the relationships between these different gases in the flasks. So on the left is the relationship between the excess CO2, the enhancement in CO2 on the y-axis, and the fossil fuel CO2 on the x-axis. Now the summer is shown, summertime points are shown in grey, and they're grey because when you try to do this in the summer, when there's a large biogenic CO2 flux, there's very little correlation between fossil CO2 and total CO2. But in the winter in Indianapolis, where it's pretty much a dormant season, there's not too much photosynthesis going on, we see a very good correlation between the two. But it's not a one-to-one line. Actually, the slope of that relationship is 1.1. So what that tells us is there's about 10% more CO2 being added to the atmosphere than from the fossil fuel emissions alone. And so that means that even in this dormant season, we've got some biogenic carbon fluxes, which we think in Indianapolis come from human respiration, also from the pets of humans, from biomass burning, and also from plants that are still respiring through winter. So that gives us a sense of the wintertime respiration flux. On the right is the relationship between the CO excess and fossil CO2. So CO is, of course, produced during combustion, and the amount of CO produced depends on the efficiency of the combustion process. So some processes produce more CO than others, and then it's also possible in many cases to scrub CO out of the tailpipe or out of the chimney of whatever process you're doing. So it depends both on the combustion efficiency and what kind of cleanup there is. But what we find in the US is that most of the CO comes from traffic, from transportation. And we see in Indianapolis, we see this very strong correlation between CO and fossil CO2, both in the summer, which is shown again in grey, and in the winter. And that has a ratio that stays pretty constant. It's about 7 parts per billion of CO per ppm of fossil fuel CO2. And the fact that that's a fairly stable ratio means that we can then use that from these flask measurements that we typically collect once a week or twice a week to translate to the high resolution carbon monoxide measurements that we can make from in situ instruments to be able to infer fossil CO2 at high resolution. So this is just one example from Indianapolis of how we apply that. We've been using this mass balance technique from aircraft to infer emissions from Indianapolis. So the concept is that you imagine your city produces emissions and it kind of is a hose pipe of a plume being transported downwind. So you fly an aircraft downwind of the city, and that's shown in the bottom left graph. You measure in the aircraft, you measure whatever species you're interested in and that you're able to measure at high resolution. This is shown there as CO2. We've also measured CO and also methane from Indianapolis. So we make a bunch of measurements at different altitudes and map out that plume. And then in this case, we used a Kriging method to basically fill in the gaps of where we didn't measure and map out where that plume is. We've also made high resolution wind measurements on the same flights. And if we know the wind speed and wind direction and what that plume shape looks like downwind, we can actually quite simply calculate the emission flux from the city. And so we did this for a series of 9 flights in 2014 over a period of a month in the winter, where we thought, well, emissions should be consistent. So this will give us a sense of over multiple flights, how much variability there is. So we did this mass balance analysis for 9 different flights. We measured the determined the CO emission flux from the whole city for each of those, and the CO2 emission flux from the whole city for each of those. Now, as we already know, there's a CO2 contribution from biogenic CO2, not just from fossil CO2. But if we use that ratio that I showed earlier of CO to fossil CO2 that we've determined from a large number of flask measurements, we can take that CO emission flux and simply scale it to determine a fossil fuel CO2 emission flux for Indianapolis for the winter. And it turns out that that number we have is in exceptionally good agreement with what we think we know about fossil fuel emissions from bottom-up inventories. So that gives you an example of how we can use radiocarbon in these kind of fairly sophisticated studies that a number of groups are doing around the world now. And the second example I have is still uses some pretty sophisticated measurement techniques, but it's a lot more accessible. So as we went into lockdown in 2020, I was going to say last year, but it's 2 years ago now, we along with many others realized that this would make a really big difference to fossil fuel emissions, and it might be the only experiment that we have where we can actually see what happens when emissions changes and see if we can detect those changes. New Zealand had a particularly vigorous lockdown, I guess I'd say, and the restrictions were very strong. Most people were not allowed to go more than 5 kilometres from their home. Pretty much everything was closed, a lot more than in other places. And I spent a lot of time on the phone and writing pleading emails asking for permission to go out and collect samples, but was not successful. So we thought about this, and we came up with this idea of doing a citizen science campaign. And we were fortunate that people were all stuck at home and they were bored. And we managed to get some national media attention and get people around the country to collect grass samples for us through the lockdown. And so the idea of this is that plants, when they grow, use photosynthesis to absorb CO2, and that carbon from that CO2 gets laid down in their leaves. And the radiocarbon content of the CO2 that's photosynthesized is faithfully recorded in the leaves. So you can measure the radiocarbon content in the plant material and infer what the radiocarbon content of the atmosphere was for the growth period of that leaf. And grass is a really good one because it grows really quickly. And if you sample the grass by cutting down to the white roots and then let it regrow over a week and sample it again, you'll have a roughly weekly sample. It's an imperfect sampling system, but it's pretty good. And these are a couple of photos of some of the many kids who collected samples for us. I think a lot of parents got their kids to do this, and you know, they wrote spreadsheets and typed in all their information and drew maps and all sorts of things. It was quite wonderful to see all the effort that went into it. We through all the media outreach that we did, we had 441 people sign up to participate in this study. Ultimately, 110 people sent samples back to us. And the map there shows samples where they came from around the whole country, and then the labeled cities are where we ended up actually using the samples. We had to do quite a lot of decisions on which samples to measure. Some people hadn't sampled every week. There were a few people who didn't sample in the same place every week. And then we had some unfortunate problems that a few of the samples, when they were sent back, it took a long time in the mail, and the grass had deteriorated to a point we couldn't measure it. And then the other problem is that quite a lot of the samples were collected in rural areas where we didn't expect that we would see a meaningful signal. So we went through all that screening process, and we ended up with 17 sites from 5 cities that we could look at. I put this figure in to show how we do it, mainly because our outreach people spend a lot of effort making this cool little diagram. You take a grass sample, you look at it, you choose some of the grass leaves. We do an acid wash to remove any surface contamination, combust to produce CO2 gas. We react that CO2 gas to make graphite. We measure it in an accelerator mass spectrometer to determine the radiocarbon content. And then the last one is that we use maths to find out how much fossil fuel CO2 is in the air. We do a lot of using maths. Another thing that we have to think about with grass sampling is, of course, grass is growing at the surface and it's necessarily within a few centimeters of the surface. So have to think about the spatial extent of the sampling methods. So this is a picture of Auckland, a very green city. What I talked about earlier for Influx, if you fly an aircraft, you can see a whole chunk of the city from the aircraft. You're high up and you're far away and you're seeing a big part of the city. If you put in a tower network, a tower might see a smaller area of the city than the aircraft does, being a bit closer in. Depending on the height, it might see a lot of the city or a small bit of the city, depending on the winds and so forth. But if you're sampling grass, you're seeing a really small bit of the city. And the challenge is that we don't really have very good modeling tools to figure out how the air is interacting in that roughness layer where the grass is growing. But we really wanted to get a sense of what the footprint of an individual grass sample might be. So we used WindTrax, which is a plume dispersion model, with some real wind data. We took 3 what we thought were representative weeks of wind data, one with low wind, one with medium wind, and one with high wind, and ran simulations for a week of daylight hours and looked at what is the influence of emissions from different distances away from that grass growing, a few centimeters from the ground. And not particularly surprisingly, we found that something like 80% of the signal is coming from within 20 meters, and it tails off very rapidly further away. So if there's no emissions very close by, then we will see emissions from further away, but primarily we're going to see the really nearby emissions. And what we did here is most of the samples, or all of the samples, came from very close to roads. So essentially what we're seeing is the signal of traffic nearby to the site within probably 20 meters most of the time. So here's a first example of measurements that we made. This is a site in central Wellington from the median of a divided city street. And what's shown is the data is the measured fossil fuel CO2 derived from radiocarbon for weekly samples taken from that site, going from level 4, which was the strictest lockdown in New Zealand, through to level 1 when COVID was eliminated successfully for about a year, and things went back to normal. And you see this very clear change in emissions. From this, because we don't understand the atmospheric transport perfectly, we can't evaluate absolute emissions, but we can look at the change in emissions. So we can look at the difference in the fossil fuel CO2 mole fraction that's shown here between level 4 and level 1 and see what the change is. Now, this sampling system didn't work perfectly in every case. Here's an example from a rural site that's about 200 meters from the nearest road, and that road is quite rural and not very busy. There is very little fossil fuel CO2 signal at that site, which is not surprising. So we can't look at changes in emissions there, but we're actually able to use that to understand background and some of the more technical details of corrections within our calculations. We had a few other sites. This is one in Wellington where the site is about 70 meters and up quite a steep hill from a busy road. And here we did see a signal, but the signal was quite small relative to the uncertainties in our measurements. So we weren't able to reliably interpret the change in emissions there. We had a few sites that we don't even know quite what to make of them. And some of them, it may be with citizen science sampling, they may be mislabeled samples, or it could also be that there's some local sources that are intermittent that cause a lot of variability. So what we did is we looked at the variability in the fossil CO2 during level 1, that when we're at the back to normal time, and if we saw substantial variability there, we said, okay, this site's got a lot of variability and sources going on, and we'll exclude it from the data set, as in this case. And nonetheless, that left us with 17 sites. So showing the results, the one at the top is the one I just showed from central Wellington. There's actually a second site just about 100 meters down the road on the same road shown on the map there. And you see with both of these, we see something like a 75% decrease in emissions in level 4 relative to level 1. And there's some interesting differences. One site is at an intersection where traffic builds up a lot more quickly, and the other site is in the middle of a street segment, and you can see some subtle differences in the changes in emissions between those two sites. Here's 3 other sites that are all on busy roads or motorways in Wellington. Again, we see a very similar kind of pattern. If we go to Auckland, which is New Zealand's biggest city, we see the same pattern, but quite surprisingly, the site at the top, which is in the central business district of Auckland, much smaller drop in emissions, and we were initially puzzled by that. But it turns out that in this area, most of the traffic, or a large proportion of the traffic, is buses. And buses continue to run right through the lockdown, whereas in all the other sites we were looking at are much more dominated by private vehicles, which weren't out driving. So this is a real difference in the emission changes at these different locations. 17 sites altogether, just showing the drop in emissions in level 4 lockdown relative to the normal level 1 period for each of those sites. On average, it's a 75% drop, but there is some variability, as I said, depending on the sites. That's probably, that is related to what was really happening at each of those individual sites. And we can compare that with some other metrics. The one on the top right is Apple mobility data, which Apple's a bit cagey about what really goes into their mobility data, but their numbers say that there was about an 81% decrease in emissions in level 4 across New Zealand, which is a little bit, it's close, but a bit higher than what we see in our observations. And of course, because Apple mobility data is not necessarily a perfect metric for emissions. On the bottom is traffic count data from Waka Kotahi, New Zealand's transport agency, from 6 sites in Auckland, Wellington, Christchurch, Hamilton, and there was no data for no measurements in Gisborne, but in another city, Dunedin. And those match up extremely well with our averages, about 75% drop in emissions in level 4. But as you can see, even though there's a lot of traffic count data, overall there's actually only a small number of long-term sites. So we've actually got more sites and more data than in the traffic counts. So we can really start to investigate patterns. All right, and I think I've reached the end of my presentation. So radiocarbon, as I said, is really useful to look for recently added fossil fuel CO2 in the atmosphere, really helpful in urban areas. And we're particularly excited at these results from the lockdown in New Zealand and being able to really diagnose traffic emissions from radiocarbon measurements. And we think that there's some exciting potential for that in the future to really look at if we can see decoupling of traffic from emissions as we reduce the emissions of individual vehicles over time. We have a lot of projects that we're involved in New Zealand and around the world, and some pictures of some of those pretty places here. So thanks very much for your attention.
Thank you, Jocelyn. A very, very nice presentation.
Thank you.
Okay, let's see. Do we have any questions from the audience?
Yes, there is one in the chat. Maybe you want to read it yourself, Jocelyn, directly?
Okay, yeah, from Patrick. At the City of Zurich, we would be interested to know the bio versus fossil part of CO2 from waste incineration. How feasible do you think these measurements would be? Yes, and there's couple of groups who have done this. The group in Groningen, Sane Polstra and others have done those kind of measurements already. If you can collect samples of what's coming out of the smokestack, it's pretty easy to do. You know, your question there is, of course, if that proportion is changing over time, how many samples would you need to diagnose what the variability is through time in those proportions of emissions? But you know, if you can collect samples out of a smokestack, it would be pretty straightforward to do.
Thank you. And we have another question in the chat.
Oh, suddenly there's a whole lot of questions.
I see too. We have one from Hans Helsen. Would you like to read it?
Yeah, so how would ethane fit into the story? So ethane is very useful in looking at methane sources. So typically natural gas contains some ethane as well as methane, whereas biogenic sources of methane don't produce ethane. So if you can diagnose by measuring your natural gas in your location what that ratio of methane to ethane is, then you can use ethane measurements along with methane measurements to infer methane. For CO2, to try to look at CO2 sources, I don't think that ethane would be very useful.
Okay, thank you. Should we take from Sam? You have Samuel Hammer, you have a question.
Yeah, hi Jocelyn, thank you for that great talk. I want to ask you a little bit about your experience which you had with Indianapolis. I think that is one of the maybe the best equipped cities when it comes to tower observations. And what you have learned from that, what would you say, what would be the most important towers of Indianapolis which you had? Or if you have only a few towers which you could place in a new city, how would you arrange them?
So absolutely for sure, the background is really important. So wherever you decide to put your observing towers, you must have a background. So for Indianapolis, which is in the middle of the continent, we had a tower that's pretty much upwind of the city, and our sampling strategy was to only sample when the wind direction was such that that tower was indeed upwind. Now that, of course, that sampling strategy means that we're only seeing the city under those wind conditions, and you could think, well, maybe a sampling strategy that sampled from different wind directions might also be helpful. But you're trading off how many samples, how many measurements can you make? You know, do you want to have a dense data set that samples one wind direction or less data from multiple directions? But that background is really crucial. If you don't have a background, it's really difficult unless you're really lucky and the background air coming into your city is consistent. But if you're in the middle of a continent, that's really hard. In terms of observing sites, I think it depends on the city. If you have a nice convenient round city like Indianapolis, you can just say, oh, we'll put towers around a nice ring around the city. But if you have somewhere that's got some more geography, or also that has some large sources like power plants or other industrial sources, you kind of need to think about where those are and how they might influence your measurements. So you also want to think about how high off the ground you are. Like obviously the higher off the ground you are, the more of a mixed signal you see that sees more of the city, but maybe less able to separate individual sources. I don't think there's not a right answer, but you sure want to think about it a lot.
Yeah, thank you, Jocelyn.
Okay, thank you. Then we have one question in the chat. Joseph Anton Morgi is asking if you separated C4 versus C3 plants, or did you know the proportion?
We did not. And one of the really nice things about using radiocarbon is that because carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14, we knew obviously plants, depending on whether they're C3 or C4, fractionate when they take up CO2 in different ways. So C4 fractionates less than C3 plants, quite a lot less. That fractionation is really obvious in C13, and it happens in C14 as well. But because there's a mathematical relationship between the fractionation in C13 and C14, we actually correct for it. So the C14 measurements are always normalized to the same stable isotope fractionation correction. So we actually don't have to worry about which kind of plants they are, is the answer.
Okay, thank you. Then we have Dario Papale with a question. Go ahead.
Yeah, hi. Thank you. Very nice presentation. My question is, do you expect that at one point this radiocarbon technique cannot be used anymore because the amount of radiocarbon in the atmosphere will be so small that the uncertainty will be too large to record the signal?
It'll have to be a lot smaller. So in the delta 14 notation, it looks like it's really small because we're now at it back to around about 0, but 0 is actually we're back at the value of our standard. So we'd have to add some mind-boggling amount of fossil CO2 to get the amount of radiocarbon too small. But it is true that over time, the sensitivity of the method is not as good as it was, but that sensitivity change is fairly modest. There's sort of a bigger problem for radiocarbon dating, where people are using radiocarbon to determine how old things are. As we keep adding more fossil fuel to the atmosphere, under the sort of business as usual IPCC scenarios, by 2100, the atmosphere will look like it's 2,500 years old. And that's going to be pretty problematic for radiocarbon dating as a dating technique.
Okay, thank you for this answer. Then we have Jishin asking, based on the equation you showed in your slides, is it possible to quantify the flux of biogenic CO2?
So the way we do that to get the biogenic CO2, we take the total CO2 enhancement over a city and the fossil fuel CO2 enhancement that we've calculated from radiocarbon, and the difference is the biogenic. So we can get the biogenic CO2 mole fraction. And if we have enough measurements, we could do an inversion or some other technique to infer the biogenic carbon flux. With flask measurements, which we have to do flask measurements for radiocarbon, we can't measure in situ. That is a bit limiting. It's quite hard to do an inversion with flask measurements because there's just not necessarily enough density.
Okay, thank you. Then we have one question from Hugo. First saying very nice presentation. And then he asks, for Indianapolis, you said about 10% biosignal. Do you know if numbers are available for a few more cities? Just guessing, but can imagine it might vary. Yeah, so this is, I mean, this whole what is an urban biogenic carbon flux is a question that we don't really know the answer to right now, and research into the biogenic fluxes themselves is a pretty new research area. So for Indy, we saw in the winter about 10%. The John Miller's study in Los Angeles was around about 20% of the CO2, 20% biogenic relative to the fossil fuel component, which was surprisingly high for Los Angeles, which you kind of think of as a very built out city. We have started to look in Auckland. It might be more substantial, but we've only thus far made daytime measurements. We haven't got any nighttime measurements, so we can't quite say for sure in Auckland. And I think there's a few other studies that are going on that are starting to look at this, but I haven't seen any numbers for other cities, but I'm sure they're out there. Okay, thanks. Then we have a question from Michelle. Do you and your US colleagues manage to sustain the Indianapolis atmospheric network? Is there interest from the city authorities? Yeah, so we have been very fortunate that the Indianapolis program is funded through a sort of special avenue that NIST, the US National Institute of Standards and Technologies, wanted to get into the greenhouse gas arena, and they have sort of a ring-fenced fund to support this urban greenhouse gas work. So Indy we continue to be funded through that. That network is expanded, so the Los Angeles Megacity project and the Northeast Corridor project are also funded from that same
pot of money, and a few other things, some of the work in Boston as well, and Salt Lake City, I think. So we've scaled back the network in Indianapolis. We've taken out a number of the towers, but we hope to continue with at least some infrastructure into the future, because, you know, now we've got more than 10 years worth of data. It seems like it would be crazy to stop and go somewhere else. You know, there's so many opportunities to look at changes, to think about how you can use atmospheric data in cities. That wealth of data that we have really gives us an opportunity, and gives the opportunity for other people, not just the people on the project, to look at that data if you have ideas or you're interested in looking at it.
Okay, thank you. Still questions? There's still time. We have another question from Jishin, and she's asking, 14C is a heavier isotope than 12C. Do you think if there would be isotopes fractionation when using biological samples, such as tree rings, to calculate fossil fuel CO2 compared to using the air directly?
Yes, so yes, there is fractionation. So all plants fractionate. As I said, related to C3 and C4 plants, it's the same thing. We measure all 3 isotopes of carbon. So we actually, by measuring carbon-13 as well, the radiocarbon measurements are corrected for fractionation, so they're all normalized to the same C13 content. So we're removing that effect mathematically, and that's a really nice, powerful technique that allows us to use plant material to determine radiocarbon in the air. And I mean, this has been used widely. You know, radiocarbon dating relies on calibration of what the radiocarbon content of the atmosphere has been over the last 50,000 years by using tree rings and other archives. So it's a very well-established method.
Thank you. Then we have one question from Maggie. First, she says, great talk. And then she asks a question about these longer time series. Is there a risk that changes in measurement technology are affecting the analysis of the data?
So for the Indianapolis example, which has been running since 2010, we have not made any major changes in the technology. The in situ instruments are Picaro instruments. We have changed, you know, instruments break, they switch around fairly often. Obviously we track all of that stuff and calibrate and all those things, but there haven't been major technology changes there. Same for the flasks, mostly using the same technology, and obviously there's a lot of effort to make sure that the measurements are accurate and they're on the same scale and all of those kind of things. I do think once you start getting to longer time series, the data that I showed from our Wellington radiocarbon record, we've been measuring that for 70 years. The technology has definitely changed, and I think that there are changes in that data and probably small changes in offsets between the record over time, and that's inevitable, I think. I guess the best you can do is to try to understand what those changes are and account for them.
Okay, thank you. We still have a couple of minutes here. So seeing if anybody wants to add something or, okay, we have one question from Claudio. Go ahead.
Hi, Jocelyn, thanks for the great talk. This is a little bit less technical, but I was wondering if you have ever scaled up the reduction in emissions you have measured over the COVID lockdown periods in New Zealand in relation to what the goal would be from New Zealand. As in, I mean, we cannot lock down a city or a country to make COP26 happen, but but in relation, you know, how much has it reduced, and would that basically be substantial to say, yeah, if we would not drive, then, you know,
yeah, so
less. Something.
Yes, so those numbers are roughly I'll just go through it. It's a bit complicated. New Zealand's unusual, but about 50% of our reported emissions are agricultural methane, because we have a very large agricultural sector. Of the CO2 emissions, which are about half of what we're reporting, traffic is something like 40% of that. So 75% reduction in traffic is about 30% reduction in CO2 emissions for New Zealand, which is our 2030 goal for the Paris Agreement. So we'd need to continue with a 75% reduction in traffic to achieve that goal from just traffic alone. Obviously, there's other things that we can reduce emissions on. And obviously that doesn't mean we have to stop driving. It just means we have to drive vehicles that don't put out as much CO2, which is not a trivial task to change the entire fleet.